My dear student, colleagues, and the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So good morning to all. Hope you are well and safe from Corona pandemic. So as you know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar. We have successfully completed our 200th international physics webinar, including 3 Nobel laureate speakers. And today it's our 201 international physics webinar. And we have with us here today Dr. Lakshmi Bala, Madam, Professor at Department of Physics, Indian Institute of Technology, Madras, Chennai, India. And she has already connected with us. So I'd like to welcome our speakers. Madam, good morning.
Good morning.
To our university through online, and thanks for accepting our invitation. So for those who are new, I'd like to inform you of that. So you can join with us through this link, and you can also ask question by commenting. And I think you have already come to know the title of this today's international physics. So the title is the Quantized Light to Operational Quantum Computing, and our speaker is Dr. Lakshmi Bala, Professor, Department of Physics, Indian Institute of Technology, Madras, Chennai, India. So I think you will enjoy this exciting webinar. So, Madam, it's your time. You can start your session.
Good morning, all of you. And thank you very much, Professor Das, for this invitation. I'm really impressed that you have already had 200 very nice colloquia talks. And it gives me great joy to start the third century and to be the opening batsman in your innings. So thanks a lot for this. I know it is pandemic time and these are very cruel times, and the education platforms are not as they used to be. We are doing many things online. But all the same, research continues in certain exciting areas across the world. This research is both theoretical and experimental. I hope to communicate to you some of the exciting aspects of a very, very important area of research and physics. And this has to do with quantum optics. I know that you are all largely BSc level students, undergraduate students. So I will try as far as possible not to assume too many things, and I will keep it as popular as I can. Please feel free to interrupt and ask me questions as I go along, except that my network connectivity today is not particularly good, and I hope that I will not get disconnected from you. Bear with me, if such a thing happens, I will try to reconnect. I chose this topic because Professor Das told me to choose something which can be explained in a pedagogical fashion, and which is also an exciting area of physics. Quantum optics itself is a reasonably old subject. In fact, quantum optics is very, very intimately connected with the quantum mechanics. What do I mean by optics? Anything to do with light. That's a very simple definition. Many of you would have studied classical optics. You would have studied interference, diffraction, polarization. What can you do with light using a lens, using a mirror, using a prism? What do you mean by the solar spectrum? Things like that. You either have already studied or you will study. Some of you would also know that light is actually electromagnetic wave. There is an electric field and a magnetic field component which is associated with light. So what is classical? What is quantum? When do you say that you're doing quantum optics? When do you say that you're doing classical optics? These are questions that need to be addressed first. before we go on to do anything more. Again, I want to reiterate that although quantum optics is closely related with the birth of quantum mechanics itself, of late, that means over the last, say, 20 years or so, there have been some very, very interesting experiments in optics and very good supporting theory. A lot of it is targeted towards quantum computing, quantum information processing. These are two very important areas of current research across the world. And that is why this topic. If you feel I'm talking too fast, please stop me. If you have any questions, please stop me and make your voice audible and ask your question. I hope you can see the next slide.
Yes. Yeah.
Good. Light has played an important role in both classical and quantum physics, is what I told you. So where does classical optics end and where does quantum optics begin? Actually, there is no clear divide. You see, certain phenomena can be explained both with classical optics and with quantum optics. Certain phenomena can be explained only with quantum optics. In both classical and quantum optics, light is a wave, an electromagnetic wave. However, if light is quantized and treated as corpuscles or quanta, these quanta are called photons. And if to explain a phenomenon you use the concept of the photon, then this is broadly in the purview of quantum optics. So you exploit the corpuscular nature of light to explain some phenomenon, and then it is called quantum optics. So largely, and again, this is not a very precise definition, largely, when we treat light as an electromagnetic wave, we believe that we are working with a classical wave. When we treat light as corpuscles or photons, we would like to think this gentleman here is Shinichiro Tomonaga, who lived between 1906 and 1979. Tomonaga is a giant in theoretical physics. In fact, he is one of the leading players in quantum field theory. He was also into writing plays for the theater. So one of the plays that he wrote was called Mitsuko Namino, which simply means Miss Photon Wave. As I told you, there is the electromagnetic wave form of light and there is the photon form of light. So he calls her Miss Photon Wave and she has got this name, Namino. Miss Namino is on the run, as you can see. You can see that lady running away. And what is happening here? This story is about a court session. Miss Photon Wave is actually a criminal who is on the run. And she is very intelligent and it is very difficult to catch her. So the judge tells the police that the lady is trapped in a particular house. She has locked herself up there. She is not coming out. But once she comes out, she is a very slippery customer. She will run away. So you do one thing, just go and stand before all the doors and windows. You open one window and try to get her out of that window and trap her and catch her. So the police go and stay around the house. They open a window. But even before they could catch her, she's on the run. With great difficulty, they manage to put her in and shut the window. The judge gets irritated and says, open all the windows. Let us see through which window she jumps out. So there are police near all the windows. They open all the windows simultaneously. And then they come back and report this amazing thing to the judge. They say, look, she ran out of all the windows at the same time. She not only ran out of all the windows, there were some regions where we never saw her. There were some regions where she was there, and we are completely confused about what is happening. And this is how Professor Tomonaga starts telling us about the properties of light or the electromagnetic wave. You see, light is a very important thing. The International Year of Light was in 2015 because that was the United Nations observance for increasing awareness of the achievement of light-based research, and its importance to humankind. Now, this is a good way, the story that I told you, is a good way to also introduce to you the various important people who worked with light. Albert Einstein in 1905 published 4 remarkable papers. Now, it is not easy. If you do research, you will realize it is not easy to publish 4 papers in a year, and that too 4 remarkable papers. It's called the Annus Mirabilis because it's a miraculous year, the extraordinary year. And what were these 4 papers about? One was on the mass energy equivalence, E equals mc squared if the particle is at rest. The other was the photoelectric effect, where if light is shone in an atomic medium, you can pull out electrons. Then, of course, the special theory of relativity, his paper on the postulates of the theory of relativity. And then Brownian motion of particles. The Nobel Prize for 1921 was given in 1922, and I will read the citation for you later, but I want to tell you also something that you would have heard from many people. If somebody is extremely good at one aspect, they will also be very good at many other aspects. Einstein was a poet, a pianist, a violinist, and he was important in telling us that matter is in the form of quanta, particles and waves, the wave-particle duality. The photoelectric effect is an experiment to show that light is in the form of quanta called photons. In fact, the title of the paper that he published, on a heuristic point of view concerning the production and transformation of light, this was in Annals of Physics in 1905. In 1966, a stamp was released by the United States government. You can see the stamp with Einstein's face on it. And the Nobel Prize citation was for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. You see, as I told you, quantum optics is intimately connected with quantum mechanics. Many conferences were held, and many important, very distinguished physicists took part in these conferences in the early days of quantum mechanics, where many things were discussed and debated upon. There were a lot of arguments, in fact, furious arguments, before actually quantum mechanics was given a proper framework. This conference that I have put up here in the slide, the 5th Solway conference, was in Brussels, and it was on electrons and photons in 1927. Many of you may know, and some of you may not know, that 17 of the 29 participants in this conference on electrons and photons subsequently were awarded the Nobel Prize. And if you look at the photo carefully, you will see Madame Curie sitting there, and she got 2 Nobel Prizes, one before this conference and one after the conference. So in fact, among all international conferences in physics across times, the 5th Solway conference is mentioned as a particularly interesting and important one. Many arguments, as I said, and the famous statement that happened, the dialogue between Einstein and Bohr on the uncertainty principle. Einstein says, God does not play dice because he does not believe in probability. And Bohr says, do not tell God what to do. All this I'm telling you to show that photons have been an integral part of quantum physics right from the beginning. Some phenomena involving light in classical optics have analogues in quantum optics. Examples the Talbot effect in classical optics, and the revival phenomenon of a wave packet of light, which means the wave function that describes the state of light revives in quantum optics. Apart from this, you also have the quantum Talbot effect, which I will mention later, whereas some phenomena can only be explained with quantum optics. An example is spontaneous emission of an atom. That cannot be explained by classical optics. I spoke to you about Tomonaga's play, where there were these windows and light escaped from the windows. And now looking back, you will realize that the windows were behaving like slits, and light ran out of the slits. And then there were points where there was constructive interference, and then there were points where there was destructive interference. And that is what the police meant by saying, at some points we could not see her, at some points she was there, we do not understand. So this is essentially slits that behave like a diffraction grating, the windows Tomonaga used to talk about the diffraction grating at some level. Now, if you look at classical optics, there is the Talbot effect in classical optics, and that has to do with diffraction gratings and revivals and so on. An important suggestion that has been made recently is that it can be used to factorize a number into its primes. So this is analogues in quantum computing also. What is the Talbot effect? Monochromatic light falls on a Ronchi grating. What is a Ronchi grating? A Ronchi grating is simply a grating with a few number of slits, about 7 slits or 8 slits or 10 slits at most per grating. So what happens? Light falls on the Ronchi grating laterally across the grating. So let the grating be in the XY plane. A grating is a rectangular frame. Y is the height of the grating. Let's say along the y-axis, you measure the height of the grating, and that is irrelevant for us. X is the direction along which we will be interested, which is the base of the grating. Light falls on these slits. When monochromatic light falls on the grating, it passes through it and travels along the z-axis. So the grating is perpendicular to the direction of propagation of light. And what did Mr. Talbot see? There is a certain distance called the Talbot distance, which depends upon the grating, the slits, the light, and so on. But at integer values of the Talbot distance, he saw an image of the grating. So at the Talbot distance, at twice the Talbot distance, at thrice the Talbot distance, he saw self-images of the grating. At half the Talbot distance, he saw an image of two identical gratings superposed on each other with a small lateral shift. At 1/3 the Talbot distance, he saw 3 images of the grating superposed on each other with the lateral shift. So there were repeated copies of these gratings and their superpositions, and that's called the Talbot effect. The reason is interference of light passing through various rules of the grating. Remember, that is what happened in Tomonaga's drama also. So here is a picture of Mr. Talbot. Henry Fox Talbot, 1800 to 1877. This picture is courtesy of the National Trust and the Fox Talbot Museum. So in honor of Mr. Talbot, there is also a museum. And Talbot invented photography. This was independent of Dagger. As I pointed out to you, even about Einstein, somebody who is very good at something is usually very good at many other things as well. So the results of Mr. Talbot's work, which he presented in a British Association meeting in Bristol in 1836, are also displayed in the Fox Talbot Museum. He was a parliamentarian, he was a landowner, he was a photographer. Now, Talbot effect was rediscovered by Lord Rayleigh in 1881. And as I said, the Talbot distance depends upon the rule width of the grating A and the wavelength of the light used. That's how you fix the Talbot distance. Here is an experiment which one of my students did for his master's thesis. What he did was he did the experiment to show the Talbot effect. He also went ahead and did a numerical simulation. Um, the green and black that you see is the Talbot image of the grating. And you see this at the Talbot distance. Now, I don't know if you can see this cursor. Do you see the cursor as I move it? Yes or no? Can you see it? On the black
Yes,
carpet?
yes. You can see.
Yes, okay.
You can
Now,
see
the
it.
red arrows are the light that is coming along the z-axis. These are the slits through which the light passes. I move here, you see, at the Talbot distance, this is the ZT. The whole distance is 2Z Talbot. At the Talbot distance, you see an image of the grating, the same original thing that you saw there. Then here at 2Z Talbot, you see it, and so on. Now, at half the Talbot distance, take a look. You see two of these. You see here you have 1, 2, 3, 4, whereas here you have 1, 2, 3, 4, 5, 6, 7, 8. So you see two gratings superposed on each other. At 1/3 the Talbot effect, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see three of these images superposed on each other. Oh, this is a numerically generated Talbot carpet. It looks very pretty, particularly if you can put colors and things on it. This is what the yellow and black that I show here on the right side is the experimentally generated Talbot carpet. Actually, we didn't do a very good experiment, but even here you can see it's not too bad. The original grating, then the Talbot distance, then twice the Talbot distance, half the Talbot distance, and so on. So this is the experimental Talbot carpet. What I wanted to point out to you is that there is this mathematical function which is 1 by n modulus of g of L comma n the whole square. And what is g of L comma n? It is this summation. This function actually defines, this is the way, it is exactly the same as the intensity function in the Talbot carpet, the light intensity function as you go along the z-axis. So I can choose an n, any integer of my choice. I can go along the z-axis in steps of L. If I did that, I don't know if you can see this figure too well. I have chosen two n values. N is 11. I have chosen n is 11, which is a prime, and on the right side, n is 35, which is a composite, which is 5 times 7. Let us look at n is 11. You go along the x-axis at discrete L. L is 1, 2, 4, 6, and so on. 3, 4, everything. I plot this function GL of n for a given n. You can easily check that if n is a prime like 11, this blue dots here is simply the intensity function that I have plotted, this GLN. It doesn't change at all. It is always at a value 1. See, the y-axis is from 0 to 2, so at half point, at 1. But you come here to the right side plot, n is 35. What do you see? At n is 5, you see the intensity dot at 5. Again, at n is 10, you see the intensity dot at 5. At n is 15, it is at 5. At n is 20, it is at 5. At 25, it is at 5. At 30, it is at 5. Now you look at 7, which is another factor of 35. On the y-axis, we are at 7. At 7, 14, 21, 28, and so on, you see a blue dot. So at prime factors of the number, you see these dots. And apart from that, wherever it is not a prime factor, nothing much happens. It stays at base level. So you see the Talbot experiment can be used to factorize primes. And in quantum computing, factorization of primes is a very important matter. Now you can ask me what is quantum about it. Whatever I have said is with the classical Talbot effect. But as I said, certain things can be done with classical optics and also with quantum optics. What are the quantum analogues of the Talbot effect? You can have revivals of a wave packet as it passes through a nonlinear atomic medium. In other words, you pass light through a nonlinear atomic medium, the wave function that describes light or the state of light comes back to its original form. Now the important thing is not at distances, but at revival times. Whatever happened at distances, at Z Talbot, at twice Z Talbot, and so on, in the Talbot effect, here it happens at times, at the revival time, at twice the revival time, at thrice the revival time, and so on. And the analog of the fractional Talbot effect is the 2 sub-packet fractional revival at half the revival time, 1/3 sub-packet, 3 sub-packet fractional revival at 1/3 Talbot, at 1/3 the revival time, and so on and so forth, where you see 2 forms, 2 clones of the original wave packet superposed on each other, 3 clones which are superposed on each other. Look here, you're now into quantum cloning. These are quantum copies. Quantum cloning is a very important aspect of quantum computing and information. We would like to produce better and better clones. Those of you who are interested in knowing more about all that I have said, you can look at this pedagogical article by Professor Michael Berry and his collaborators. It's called Quantum Carpets, Carpets of Light. So what are the other non-classical effects? As I told you, there are wave packet revivals and fractional revivals. Then there is a very important non-classical effect. It's called squeezing and higher order squeezing. What do you mean by squeezing? You see, you do an experiment in classical physics, any experiment where you measure the spread in the position x. Let's say you oscillate a pendulum, and then you take readings, and then you take the average value of the displacement, and then you take the spread or the variance, delta x. Then you also find out the momentum of the pendulum. You take various values, you take the mean, and then you take the variance or the spread. I'll call these variances delta x squared and delta p squared, x standing for position and p standing for momentum. Any spread is either because of a systematic error or because of very rickety apparatus that you have got and you are doing the experiment badly, and so on and so forth, or because of the experimental conditions. Whatever it is, delta x and delta p have no relationship with each other. That is the first statement. The second statement is, by bettering your experiment, you should be able to lessen the spread delta x and lessen the error delta p. That's the second statement. The third statement, you can repeat measurements on the same pendulum. You can take the same system and keep on repeating measurements. Now in quantum physics, none of this is true. Measurement is a very important aspect of quantum physics. That's because of something called quantum superposition, and I will get to that later. But now let me tell you what is squeezing. If you make a measurement of x and p in quantum physics on a quantum system, using the methods of measurement in quantum systems, you will find that delta x, delta p product should be greater than or equal to h cross by 2, where h cross is h by 2 pi, and h is the Planck's constant. This is an important aspect. The point that I'm trying to make is that if you had the best of experiments, still, if you make delta x 0, delta x delta p should be greater than or equal to h cross by 2, and therefore delta p will become so large that the product delta x delta p is finite and greater than or equal to h cross by 2. It's not possible to simultaneously get the values of x and p to infinite accuracy. Simultaneously. The word simultaneously is very important. You can do it successively, but not simultaneously. Now, it turns out squeezing means delta x less than this 1 by root 2, root of h cross by 2, or delta p less than root of h cross by 2. This is the Heisenberg uncertainty principle, which is not violated at all Because if delta x is less than root of h cross by 2, delta p will compensate. It will become greater than root of h cross by 2, such that the uncertainty principle is not violated. You say that there is a squeezing in position if the spread in x in the quantum experiment is less than root of h cross by 2. You say that there is squeezing in momentum if in the quantum experiment delta p is less than root of h cross by 2. As I said, there will be compensation. If x is squeezed, p will be dilated. If p is squeezed, x will be dilated. So this is another non-classical effect, which is genuinely different from classical physics. Squeezed light has been produced in the lab, and squeezed light is very important, particularly in the context of gravitational waves, which have also become very important area of research in recent times. Then there is quantum entanglement. You can also have classical entanglement, but quantum entanglement is a very different and unique phenomenon because the aspect of measurement in quantum physics is going to do something very different when there is entanglement in quantum physics compared to the act of measurement in classical physics. So I have given you a list of 3 interesting non-classical effects. All 3 are useful in optics and in optical quantum computing. Now, I told you that many of these depend on quantum superposition. Let me come to light. What do I mean by quantum superposition? You know that the electromagnetic wave has 2 polarization states. Now, these 2 polarization states, when I do quantum optics, these are related to the fact that the photon or the corpuscle of light has spin 1 with 2 polarization states. So when you talk of quantum optics, you talk of the polarization states of the photon. Let me denote these by the state H and the state V. You can treat these as qubits. That means analogues of classical bits 0 and 1. When you do electronics, you would have heard of classical bits 0 and 1. You would have done experiments with them. These are quantum bits. I'm giving you an example of quantum bits. The polarization states of the photon are quantum bits. As 0 and 1 are very distinct from each other, state H and state V are very distinct from each other. If you wish, you can think of them loosely as the unit vectors I and j on a plane. You know that I is very distinct from j. You know that I dot j is 0. And you also know that any vector in a plane is written, for instance, as 5i plus 4j or something like that. Similarly, any state of light, polarization state of light, is written as some number times state H plus some number times state V. At this level, it is like some A times unit vector I plus B times unit vector j, except that I'm doing work with a qubit or the quantum polarization states of the photon. So as I said, a general polarization state can be in a superposition of state V and state H. I've written it as some C1, some number times state H, plus C2 times state V. Now, what is new about the measurement in quantum physics? Unlike classical physics, when you measure the polarization, I don't know what is C1 and what is C2. I take a state, I take a polarization state. I make a measurement to find out the polarization state. In quantum physics, the state will collapse to either state H or state V on measurement. This is very different from classical physics because I cannot do a second measurement on the polarization state using that original polarization qubit, because it has already collapsed to state H. When I do a measurement, I will get state H. If I do a third measurement, I will get state H. Therefore, I need to use an ensemble or identical copies of this polarization qubit. I make a measurement of the polarization state on one qubit, get that value, maybe it is state H, I throw it out. I make a measurement on the second qubit, maybe it is state H or state V, I jot that down, I throw it out. I take the average of so many measurements and tell you what is the probability of being in state H and what is the probability of being in state V. This is the basic difference in measurement in quantum and classical physics. I have a cartoon for you here, and this is the Schrodinger cat, about which many of you might know. There is this trap, and this trap, this cage has this cat, and this cat is starved. So you don't know at the end of 14 days whether the cat is alive or dead. It is in a, look at the red line here, it is in a superposition of the dead state and the live state. What is this is what I know before I do the measurement. What is the measurement? The measurement is open the trap and take a look at the cat. Now, when you do this measurement, you know whether the cat is dead or whether the cat is alive. So it will collapse to one of these states. So this is called the Schrodinger cat thing. And this is quantum superposition. And you can do single photon experiments these days for logic gate operations, treating the polarization qubit as the superposed state of polarization. Make measurements on this, treat qubit state H and qubit state V as two different things, and use them like you would use bits 0 and 1 and do logic gate operations. So this is the whole idea of logic gate operations. An ideal platform provided by quantum optics is also the interaction of photons with atoms. There are very nice experiments these days with 2-level, 3-level, and multi-level atoms. And you have to work in quantum physics, therefore you use photon creation and destruction operators and do this job, a matter which I will not go into great detail here. What are the various states of light that I can have? An example is ideal laser light. Now, when you switch on laser light, many of you might not recognize that this is coherent light. Usually, we denote it by this in Dirac notation. This is called a ket. Dirac gave us this notation. You put an alpha there because mod alpha squared, alpha is a complex number, and mod alpha squared will give you the intensity of light. So I can produce laser light in the laboratory, and that is coherent light, ideal coherent light. It is coherent. If I add a photon to it, how do I add a photon to it? What kind of experiment? Well, I get laser light to interact with an atom. The atom could be in its excited state. You would have heard of stimulated emission. This light will stimulate the atom to release a photon. The atom will go to a lower energy state. What happens to the photon? The photon gets absorbed by the light. Then you have a one photon added coherent state. It is no longer ideal coherent light. It would have departed from coherence. If I have a group of atoms, I can tickle various atoms in the excited state, get them to emit photons through stimulated emission. The photons will join up with the original light, and you can have a 2-photon added state, a 3-photon added state. But remember, you're losing coherence with the addition of each photon. But if I have to understand this in terms of corpuscles of light, how do I understand laser light? Before I go there, let me tell you what happens with coherent light. I don't know if you see this picture. This black parabola here is where the light is. This is the electromagnetic wave. I have plotted it. It is E squared plus B squared. So this is the energy, and I've just plotted it. So if I take light which is coherent, it behaves like a classical particle. Look at that dot. What will a classical particle do if it is trapped in a parabolic well? What will a classical oscillator do? It will go from this end. The green line tells you that energy is a constant. That is the value of energy that I give. The ball moves from here, there, and there, here. If you look at the inset, the ball goes and hits the wall. I have just expanded one part here. This part is expanded there. The ball goes and hits the wall, oscillates, goes back, hits that wall, oscillates, comes here, oscillates, goes there, comes here. This is what coherent light will do. If you add a photon, even a single photon, what happens? The waveform will not touch the edges. Somewhere here it will stop. That's what I mean by the ball there. If you add 2 photons, it's even worse. The more the number of photons, it will oscillate very, very locally here and not go through the full distance. This can be numerically simulated as an experiment in a laboratory and demonstrated. But as far as experiments go, only the single photon added coherent state has been produced till now in the laboratory. That happened in 2005. They have not produced 2 photon added states yet. These are difficult experiments. But if I want to talk about ideal light, laser light, and in terms of photons, what is it? As I told you about superposition, now not polarization superpositions, but superpositions of photons. It is an infinite superposition of photons. You have a 0 photon state, a 1 photon state, a 2 photon state. It contains all possible photon states. If the laser light has very, very low intensity, it has a very, very high probability of having only a single photon. So what kind of experiment can I do with laser light which has very, very low intensity? Well, I can do many things. Since it is a single photon, or the probability that it is a single photon is very high, I can look at the polarization states of the single photon, treat the 2 polarization states H and V as qubits, and do logic gate operations. That's what I meant here when I say photon quantum computing. What about squeeze states of light? I did explain to you what is a squeeze state, but I have a cartoon here. As I said, if there is squeezing in X, then there is dilation in P. Look at Tom here in the Tom and Jerry cartoon. The poor guy is pulled out here, but squeezed here. You see, if he's flattened here, then he becomes very, very big, so that there is compensation in the other direction. So this is just a cartoon to show you that squeezing in one form is going to dilate in the other form. I believe I have explained this considerably, as popularly as possible. And you could look at Tom and the way he has been squeezed to get just a funny picture of what squeezing is all about. I told you that very many interactions can be carried out, can be arranged in the laboratory between atoms and light. This is an example. This system actually demonstrated something very interesting: electromagnetically induced transparency in quantum physics. What does that mean? First of all, in quantum physics, people keep talking of cavities. What's a cavity? You have to trap light. In order to do an experiment with light, you have to trap light. Otherwise, light will spread like Miss Photon Wave in the Tomonaga theater play. You want to contain light, you keep it in a place. You use a cavity. What are cavities? The blue thing here is a cavity. Means mirrors. Use mirrors. Use Snell's law. Reflect the light back into the region contained within the cavity. So you trap light by using mirrors. So the cavity is just a set of mirrors. Now you have trapped light. What will you do next? You can put an atom there. Now I have an atom which is a 3-level atom. There is a ground state, then there is another state, and then there is another state, and they're all very different in energy. You can contain a 2-level atom there, a 3-level atom there. You can do many things. You will tell me, but how do you know that the atom has only 3 levels? I mean by 3 levels, I mean 3 relevant levels. That means these 3 energy states are close to each other. By putting it with light and making the atom interact with light, I can arrange for these arrows. That means transition from one state to another. The electron in the atom can jump from that state here, from this state there. It can jump from number 3 to number 1, from number 1 to number 3, and so on. In this arrangement, 1 to 2 transition is not possible. It's called a lambda atom because of it looks like the Greek alphabet lambda. An example of a lambda atom is rubidium. Rubidium atoms are used for experiments which involve quantum optics because a photon is absorbed and it goes from level 2 to 3. The photon is emitted, it goes from level 3 to 2, and so on and so forth. So it's filled with light because of the cavity, it is trapped there. The atom is also trapped in the cavity, and you can conduct this experiment. Such experiments are conducted. Then you can have the double-well Bose-Einstein condensate. This is not an experiment in optics, but I can have 2 atoms out here, and each atom can stay in different energy states. And there is a trap. This is a well, a potential well in which the 2 green atoms, by green I mean just the color that I have used, atoms A and B are trapped. And these 2 can interact. The atom can jump here, the atom can jump there, all this can happen. And you can have revivals of the full state and so on and so forth. So 2-level atoms interacting with radiation fields. It's possible that this one, by radiation field I mean light. This atom can interact with one field, that atom can interact with another field. So all kinds of arrangements can be made to make light atom interactions possible. Then there is cavity optomechanics. What is that? Lovely experiments, where light is trapped in a cavity. There is a 2-level atom here. One of the mirrors, this one, is capable of small movements, small oscillations. Like a simple harmonic oscillator executing very small oscillations. Why does it oscillate? Because of the radiation pressure that builds up inside the cavity and pushes the mirrors. This one is kept fixed. It doesn't move because of radiation pressure. This one can move. What have I attached to it? I have attached a mechanical spring. To the spring is attached this brown light membrane, a very, very thin, almost massless membrane. Because of the radiation pressure, there can be atomic transitions. The atom interacts with the light. And the radiation pressure pushes the mirror back and forth. And therefore, this membrane oscillates back and forth. These are mechanical oscillations. This part of the setup is mechanical. What happens between the atom and the light is optical, because light is absorbed and emitted by the atom. So 2 things happen here. The light interacts optically with the atom, and it also pushes the cavity and allows for a mechanical motion of the membrane. And that is why this is called cavity optomechanics. Cavity optomechanical systems are very, very useful. Squeeze states, etc., are produced there, and beautiful experiments are done, which are potentially useful for quantum computing and information processing using optomechanical devices. So I have given you many different types of setups One is cavity optomechanics, one is just a lambda atom in a cavity, through which electromagnetically induced transparency is demonstrated, and many nice experiments are done. This is not optics, but this is a double well Bose-Einstein condensate, which too shows non-classical effects. So a rich variety of experiments can happen. So I want to talk a little bit more about entanglement. For entanglement, you need two systems at least, or rather, if you think of a full system, you need two subsystems at least. You will need two photons or one atom and light. So the light is one subsystem, the atom is the other subsystem, or you will need two atoms. So you will need two objects. These could be two atoms or two light fields, or one atom and a light field, at least two. There could be three, four, five. Entanglement can happen between two systems, or three, or four, or five. So minimally, you will need two systems. And in a bipartite system, that means there are two subsystems. Quantum entanglement can take place. So when you do atomic physics or atom optics, you will be talking about interaction between the atom and the field, which is light, and so on. Initially, the states may not be entangled. What do I mean by that? Very simply speaking, I mean the following. If I do something to the atom state, it will not affect the light state. If I do something to the light state, it will not affect the atom state. That means it is unentangled. If it is entangled, when I make a measurement on one of the subsystems, it will affect the other subsystem. You see? Go back to your familiar vectors. If I write 5i plus 4j, and if I change this 5 to 6 along the x-axis, why should it affect 4, which is along the y-axis? But here, when I say entangled, I mean that when I make a measurement on one state, it is going to affect the other state. And this is a very crucial input for quantum teleportation, because there will be two entangled states kept perhaps far away in space. But if you do something to one state, the effect will be seen in the other state. This is very important in quantum teleportation, quantum information coding, and so on. How do you produce entangled states? The beam splitter is an object which can be used to produce entangled states from two unentangled states. You can also have two entangled Talbot carpets. Now I'm returning to what I said earlier because this is the last part of my talk. But what is quantum about these? What is quantum is this? As I said, quantum means you work with photons. You work with a nonlinear crystal. Usually we use beta barium borate. Shine light on it. What does a nonlinear crystal do? It takes a single photon and maybe your frequency omega, the electromagnetic wave has frequency omega associated with the single photon. It creates two photons from this, each with frequency omega, so that omega plus omega, each with frequency omega by 2, so that twice omega by 2 is omega. Why is the frequency
dear student and viewers, we are very sorry to inform you that we have lost our connection with our speaker. We are trying to reconnect. Please stay with us. And thanks again for supporting us.
Can you see me now? Can you see me now? Can you hear me now?
Yes.
Oh, okay.
We
I
can
don't
hear
know
you.
when did we lose connection. Let me show you the slide. I will share.
Yeah,
Okay,
yeah,
let me
you can
just share
share.
screen. Yeah. Yeah, can you see the screen?
Yes, we can see. Maybe the
Yes,
previous page. Could you go back the
maybe
previous
the
page?
previous page. Okay, fine.
Yeah,
Maybe this?
yeah, this one. Yeah,
This
this
one.
one.
All right.
I think we have completed this. Yeah.
We've completed this. We are on this next one. Okay. So as I said, how do I produce entangled states from unentangled states? One object that I can use is the beam splitter. That's a very simple object, and I will get to that. But before that, I also want to connect up with what I said earlier because we are in the last part of the talk. I spoke to you about Talbot carpets. Now I want to tell you about entangled Talbot carpets. What is quantum about these things? The quantum part, as I said, comes through photons because I use a procedure called spontaneous parametric down conversion, SPDC, to produce these photons. What is this? We use nonlinear crystals, nonlinear optical media, usually beta barium borate. You send a single photon through it with the frequency omega and therefore energy h cross omega. What the nonlinear crystal does is it creates two photons out of it, uh, maybe with the same frequency, each with frequency omega by 2, so that the final energy is h cross omega by 2 for one photon and h cross omega by 2 for the other photon, adding up to h cross omega. So energy conservation. If it is non-degenerate, then one of the photons that is produced can have energy h cross omega 1 and the other one can have energy h cross omega 2 such that omega 1 plus omega 2 is omega. Always there is energy conservation. What happens to these two photons? When you use an SPDC procedure, the two photons that you generate from the single photon are already spatially entangled. They are bond spatially entangled. This is not an entanglement in the polarization states. It's an entanglement in space. What does that mean? If I tinker with one of the photons, wherever it is in space, it is going to affect the other photon. wherever it is located in space. Then what do? You can do the following thing. Look at the picture on the right. I have this source, SPDC source. I have the source of light. I pass it through this nonlinear crystal. A single photon, red arrow, splits into two photons. They take two different paths, A and B. They may go along different paths, but they are entangled. Then I use mirrors, the black inclined things, Snell's law. The two photons are made to fall on a D-slit aperture. So you see this aperture, if you count the number of slits, there are D of them. So this photon falls on this aperture. Photon A falls on this aperture, DA. It's collimated with lens. There are two lenses, one on each path. Falls on a diffraction grating. That's important. This photon, the light falls on grating G sub B, and the light falls on G sub A. Again, you use things to focus, and then there is the screen. This screen, which includes SCB and SCA, let us say is in one plane. And the first photon creates a Talbot carpet here. As you know, the Talbot carpet happens at certain distances. So at this distance, I can see a Talbot carpet. Similarly, here I can see a Talbot carpet. Now, you may imagine that these are two different Talbot carpets because they came from two different photons. But I told you that they are spatially entangled. So in fact, these carpets are entangled. They may be at different, on different screens, which are separated from each other. But if you do some experiment, if you tinker with the carpet here, it's going to affect it here, and so on. So you see, apart from polarization entanglement, I have also spoken to you about spatially entangled photons. So you can create different types of entanglement. Now you look at this beam splitter that I have a picture out here. A beam splitter is here. This is the beam splitter. It has two input ports. Through one port, I send light. And through the other port also, I send light. Either I could send light or I could just keep it as a zero photon state. So I send either a one photon or two photons or whatever through one port. Again, through the other port, I send light. Now, look at the light that comes through A. What does a beam splitter do? It partially reflects and partially transmits. So light coming from A, or if you think of it as a photon, the photon is partially reflected and goes to C and partially transmitted and goes to B. Whereas if you look at light from B, it is partially reflected and goes to D and partially transmitted and goes to C. So what is it that comes in C? What arrives at C is both light from A and light from B. In one case, it is reflected. In the other case, it is transmitted. Similarly, if you look at light from D, it has contributions from both. Now, it turns out you have used two subsystems, A and B. As I said, for entanglement, you must use two subsystems. If you look at the final state of light in C and D together, these are the two output ports, you will find that it's an entangled state. Most of the time, for most forms of light, here it is unentangled. They come from two different sources of light. Then here you will find that they are entangled. And if you do anything here, it's going to affect that. And if you do anything there, it's going to affect this. And mind you, port C and D are spatially separated. That is what entanglement does. So in long distance communication and all that, it's easy now to realize why entanglement becomes very important. But this also gives you a very interesting statement. If I use a single photon in quantum optics along A and no photons along B, this photon is going to get transmitted to C by reflection and transmitted to D through transmission. A single photon can interfere with itself. You see, that's a remarkable thing. So beam splitters are used to show a variety of experiments, and they are important aids in quantum computing and in quantum information processing. I have given you these two setups to talk of entangled Talbot carpets and how to produce entangled states in general. So just to get back and connect up, the first photon was in a qubit state, a polarization state, A times state H1 plus B times state V1. The second polarization qubit is A times state H2 plus B times state V2. So the first is a superposition of its polarization states. The second is a superposition of the second photon's polarization states. What's an unentangled state? This is an example. State H1 times state V2. I have chosen one polarization state of the first photon 1 and the polarization state of the second photon 2. No doubt there are two subsystems, but these are unentangled. I can write it as a product of something to do with the first photon alone times something to do with the second photon alone. Whereas look at this is an entangled state. State H1, state V2, if we stopped here, yes, this is only the first photon and this is only the second photon. But there is an extra term, state H2, state V1. I cannot write this whole thing as something which is only the first photon's properties times something which is only the second photon's properties. So this is an example of an entangled state of polarization, the green one, and the brown one is an example of an unentangled state of polarization. And I told you that the beam splitter can be used to create entangled states from unentangled states. So, where are we now? I'm going to conclude with some take-home lessons for you. Let me therefore summarize what I said. Quantum optics uses photons or light quanta to describe various phenomena involving light, atom-light interactions, and so on. Non-classical effects, which means effects that you can't produce in classical physics, such as wave packet revivals, squeezing, quantum entanglement, etc. Mind you, I can have classical entanglement. That's a very different matter altogether. Quantum entanglement, etc. can be exploited to carry out different quantum information processing and computational tasks. Entanglement involves at least two subsystems of a full system, and the qubits or higher dimensional objects of the two subsystems are entangled. Example, polarization qubits of the photon, or spatial entanglement between two photons, etc. Different non-classical states of light can be exploited to do a variety of optical quantum computation tasks. If you understood nothing much of what I have spoken about, this summary should at least tell you what the essence of what I said was. Thank you very much for a patient listening. Thank you, sir.
Yeah, thanks, Madam, for your wonderful and exciting presentation. So we have got few questions in the comment section inbox. So if you allow, we can start our discussion session.
Can we just have the questions told audibly, because I'm not able to see the comments easily here?
Yes, I'll read it. So the first question, what is the quantum teleportation?
Okay, so quantum teleportation means, normally you talk, look, in the literature they talk about Alice and Bob. So what do Alice and Bob do? These are two friends who share a qubit. What is this qubit? It could be the polarization state of two photons which are entangled. So Alice has one qubit and Bob has another qubit. As I said, this believes in entanglement. So Alice and Bob are separated away from each other, but they share an entangled state. What does Alice do? Alice puts in some information in her qubit. Because of the entanglement, when Bob makes a measurement on the shared qubit that Alice and Bob share, when Bob makes a measurement, it affects Alice's qubit. In other words, he should be able to get the information out. Whatever Alice has encoded and teleported to Bob, now two things can happen. Alice can send this information through a classical channel to Bob. Now you don't know if there is an eavesdropper or a hacker on the way. The eavesdropper is usually called Eve, okay? So a hacker might try to get the information during transmission. But the transmission, the information is encoded in qubits. What happens in quantum physics is this. Bob will know by comparison later when he makes a measurement, he will know whether there is tampering or not, number one. Second thing, he will also be able to see how much of the information that Alice sent has come to him, to what extent it is cloned, to what extent the information Alice gave has been teleported truthfully and correctly. So that is what quantum teleportation means. It means using shared qubits to send messages across distances in such a fashion that the receiver knows to what extent the sender's message is faithfully transmitted to him, and if there has been a hacker or not in between transmission. That's what is quantum teleportation.
Yeah, thank you, madam. We have another question. So, next question: do photons have mass?
Photons do not have mass. Photons do not have mass, and that's for a very nice reason. From a theoretical point of view, theoretical physicists like to describe electromagnetism and other fundamental interactions like strong interactions, weak interactions, gravity, and so on, using something called field theory. Field theory is it's a mathematical thing. In order to extract meaningful results from this mathematical machinery, you need to have certain symmetry properties in the original equations of motion, if you wish. These are called gauge symmetries. Now, if you demand these symmetries, in theory, the photon cannot have a mass. That's from a theoretical point of view. Experimentally, photons do not have a mass. You know that the Einstein energy relation tells you that E squared is P squared C squared plus M squared C to the 4. So E is positive square root of P squared C squared plus M squared C to the 4, where C is the velocity of light in vacuum, and M is the rest mass of the particle. If the particle is massive and at rest, it follows that E is root of M squared C to the 4 or MC squared. If the particle is not massive, like the photon, E is root of P squared C squared. In other words, E is PC. So the photon doesn't have a mass. It is born in flight, carries a velocity, and that's all that it has.
Yeah, thank you, madam. We have another question. So, is neutrino theory of light, which proposes a photon as a composite particle formed of a neutrino
does not give neutrino does not give the theory of light. Neutrino is involved in weak processes. The photon is involved in electromagnetic processes. Neutrino does not give the theory of light. No. You see, there are 4 fundamental interactions in terms of which you can describe various forces. One is the strong interaction, and the corresponding force is the strong force. An example of the strong force is what happens in a nucleus. You see, when protons and neutrons bind together, the fact that the nucleus doesn't fall apart, all this is because of a strong force. Neutron doesn't carry charge, proton carries charge. So the strong force that binds the neutron and the proton does not depend on electric charge. Now, if you look at electromagnetism, electromagnetic forces exist only between charged particles. The neutrino does not carry charge. Now, you can ask me, if electromagnetic forces can happen only between electrically charged particles, how does the photon come in? The photon is the probe of electromagnetism. What does that mean? You go to the laboratory, and then suppose you were doing experiments with charged particles. You would have read something about this. Suppose there is a charged particle like a photon, and in the scintillation counters and things like that, you see the track of the particle. If the particle is subject to an electromagnetic field, it will deflect in its track. What does that mean? The photon, which is the quantum of the electromagnetic field, is interacting with the charged particle and making it deflect in its track. Whereas if you have a neutral particle, the neutral particle is not going to deflect in its track or in its path because of the electromagnetic field. So the photon is the probe of the extent of charge. Neutrino is chargeless. It cannot, therefore, it cannot interact electromagnetically. It is not the probe of electromagnetism. On the other hand, it can interact weakly with particles. The photon cannot interact weakly. Neutrinos can interact weakly, but they cannot interact electromagnetically. That means that neutrinos cannot interact strongly, they cannot interact electromagnetically. That is why they pass through large chunks of matter without getting deflected and without us knowing, without getting absorbed in the matter. That is why when you do neutrino experiments, you do it deep inside mines. Because by the time that distance is covered, charged particles will go through interactions. Strongly interacting particles will go through interactions. But the neutrino will travel like as if it saw nothing. It will travel through chunks of matter all the way to large depths downstairs, into deep mines. And then you have gotten rid of the strong and electromagnetically interaction particles, and you can do neutrino experiments. So for the same reason that neutrinos do not carry charge, they cannot give you the theory of light. So there is no neutrino theory of light. Neutrinos are involved in weak physics. They are very important objects in weak physics with very nice properties. So that is the story of the neutrino, and this is the story of the photon, and they are two different objects. By the way, a neutrino has spin half. A photon has spin 1. Even spin-wise, they are very different.
Okay, madam, thank you. So we have another question. So how can we observe a single photon interference? How can we generate a single photon experimentally?
Young's double slit will do. You just send a single photon, and if there are many slits, then the photon, Miss Photon wave ran through all the slits, you see. I mean, in a house, in a room, if you open 2 windows, the light will go out of both the windows. So think of these slits as windows. And then you see the light comes out of 2 different, the photon came from a single source, but when it falls on the slit, it is going to come out of both the slits. And they are on different paths, and 2 electromagnetic waves can interfere and produce interference patterns on the screen. And that's how you know, and there'll be constructive interference and destructive interference. That is why you say that it interferes with itself. That is how it happens. So a double slit experiment will do the job. So there is this thing called the Young's double slit experiment. You can do it with various particles, photons, electrons, so on. So, and you can see the differences. So that is, any experiment with 2 slits will teach you that. If the source is a single photon, it is going to run out of both the windows, both the slits, along 2 different paths which will interfere. That's how you do the experiment.
Madam, thank you. So we have another question. So what is the polarization state of an ideal single photon?
Before you make the measurement, it is a superposition of 2 polarization states. I'm not in a position to tell you whether it is this polarization state or that polarization state. It is some A times polarization state H plus B times polarization state V in normal notation. Once I make the measurement, it will collapse to either H or V. In quantum mechanics, the important thing is this. The measurement told me that it is in a state H. But that doesn't mean that before the measurement, before the experiment was done, it was in the state H. You see, this is the difference between classical and quantum physics. Measurement is very different between classical and quantum physics. In classical physics, you imagine you're doing an experiment, say with a simple pendulum. You're going to find the period of oscillation of the pendulum. They give you just one pendulum in the laboratory. So you will take that pendulum and you will oscillate it. You will do the first trial and you will get a number and you will put it down in your record notebook, in your observation notebook. The same pendulum, you will oscillate it the second time. And then you will take down that number in the record notebook. Now, people have told you, you must take the average value, which means you must do a lot of trials. So you will do this experiment on the same pendulum, that one pendulum that they gave you, right? And then you will take the average. You will add all these numbers that you've recorded and divide by the number of times you did the experiment, take the arithmetic mean, and you will report it to your professor and say, this is what I got. Now, in quantum physics, unfortunately or otherwise, if I do the measurement on a single quantum system, it will collapse to one state. Let us say if I were doing polarization measurement, it will collapse to the state H, let's say. You took a single photon. You don't know what the polarization state was. It's a superposition in general. It collapsed to the state H. Now, repeated measurements on this is not going to help, because after collapse, it is not identical to the copy before collapse. Before collapse, it was in a superposed state. The act of measurement collapsed it to one of the two states. So you have to discard that copy. But in your record notebook, you will write first trial state H. Then you will take another photon. It's also in a superposition of the two polarization states. But when you make a measurement, it could collapse to H or V. You please write down H or V, whatever you note, as a second trial. Discard that photon. Take the third photon. So you have a collection. You have an ensemble. On each member of the ensemble, you will do the experiment only once. After that, there is no point doing that experiment on that copy. It will keep on giving you the same answer. Then what do? Let us say you have done 100 measurements. That means you have used 100 photons. Okay. Now, 75 of these measurements gave H and 25 of these measurements gave V. Then you will say 3/4 probability H, which means 75 by 100 H, and 25 by 100. That means 1/4 probability of V. So that is how you will say this photon has 3/4, the polarization state has 3/4 probability of being in H and 1/4 probability of being in V. That is how you have to do the experiment. So the very experimental procedure in quantum physics is different from classical physics.
Thank you, madam. We have another question. What is the second order correlation function in case of a single photon? How it differs from the first order correlation?
The important thing is this. The first order coherence function for all the photon number states, for thermal light, for ideal laser light, for all of them, it is 1. But if you look at the second order coherence function, you will be able to see a difference, because for both the 0 photon state and the 1 photon state, you will find that it is 1, but it is different as you go for higher photon states. The second order coherence function will be a function of n, where n is the number of photons. So we use the second order coherence function or the second order correlation function to see the difference between, to see whether it is a higher photon state or a 1 photon state. With the first order coherence function, everything gives you 1. The laser light gives you 1. By the way, thermal light, which means, you switch on the tube light. That is thermal light. Thermal light will also give you 1. It's only the second order coherence function which will give you a different value. If you look at squeeze light, that too the first order coherence function will give you 1. But if you go to squeeze light, the second order coherence function can give you 2, can give you other things also, depending upon the parameters that are involved. So to answer your question, depending on the number of photons, the second order coherence function will change. And that will tell you whether it is a 0 photon state or a 1 photon state. That's your question, right? Or a higher photon state. It depends on n, the number of photons.
Thank you, madam. This may be the last question. So how can we entangle an electron with targeted electron?
You can do different entanglement experiments. You can do spin entanglement. You see, that's the kind of thing that you have in these resonance experiments, an electron is a spin half particle. So you can talk of spin qubits. You would have heard that it exists in the spin state up or in the spin state down. Normally they say spin up and spin down of the electron. So instead of H and V, when you talk of the electron, you refer to it as up and down. So what is the spin? So what is relevant here is the spin qubit. Okay. So you can take the spin qubit of the first electron to be A times upstate plus B times downstate for the first electron. For the second electron, some C times upstate plus D times downstate. Now the question is, how do you entangle these spins? Obviously, for entanglement, you should use one of the spin states of the first electron, either spin up or spin down, and one of the spin states of the second electron, either spin up or spin down. So when you entangle, you can have four basic types of entanglement. Spin up of the first electron will spin up of the second, spin down of the first electron will spin down of the second. But you see, those can be factored away. What you should really do is spin up of the first electron with spin up of the second plus spin down of the first electron with spin down of the second, or spin up minus spin down, or spin up of the first with spin down of the second plus or minus spin down of the first with spin up of the second. So you can have four basic states. These are called the Bell, and you can show that you can create maximally entangled states from these. Now to answer your question, how do I produce either or any basic states for the electron? The electrons interact through the photon. So what do? You take these two electrons, interact with light. Through the interaction, you can produce entangled spin states of the two electrons. That is the way you will do it. Both the electrons will interact with each other through the light. So basically, it's an electron photon interaction. And the spin states of the electrons will get entangled. That is how you do it. That's a simple way of doing it.
Thank you, madam, for your wonderful presentation and discussion session.
Thank you very much. I enjoyed it.
Program, yeah, we have already did our 200, and this is our 201 International Physics webinar. So the main aim of our program is to motivate our students, and as you have already explained, the quantized light and optical quantum computing like a very basic way, and I think it will encourage some of our students, and in near future they might join in this research field and develop this field. So thanks again, madam, for accepting our invitation, and bye for today, and hopefully in near future we'll arrange another webinar with you, and after it we'll definitely invite you for a face-to-face session in our university. Bye for today. See you.